nanohub.org.
Okay, so the second lecture, we're going to talk about how to achieve a scanning tunneling microscope, how to actually build one. What are the considerations that you need in order to make such a microscope work? Okay, again, as a brief review, this is the schematic diagram of a scanning tunneling microscope. What you do is you set up a tunnel current between a sharp tip and a conducting substrate. The separation between the tip and the substrate is on the order of 1 nanometer. When you bias the tip with respect to a substrate and you bring the tip that close to the substrate, there's a vacuum gap whose thickness is about 1 nanometer. Electrons will flow from the tip to the substrate. And by monitoring how the current varies as a function of position, as the tip is rastered across the substrate, you can actually map out in great detail the surface structure of a substrate. Now, what might affect the local density of states of the substrate that would cause the tip motion to vary in z direction, right? And there are a lot of things. And all of these things are really important to know if you're starting to engineer and build devices at length scales that are submicron, right? So things that might affect the tunnel current that you would be sensitive to with this scanning tunneling microscope, right? You would be sensitive to atom positions, step edges, terraces. You could be sensitive to reconstruction of atoms on surfaces, because when you create a surface, the atoms are no longer in their official lattice sites, they relax. They go to a different location to minimize energy. That's referred to as reconstruction. You can start to look at grain boundaries, adsorbates, impurities, defects, dislocations, vacancy, all these things which you could not access prior to scanning tunneling microscopes now become accessible using this technology that we call an STM. Okay? What I like to do is I like to just summarize a few early successes to try to give you a sense of the impact that this microscope had. There's a question.
Going back to the previous slide, you talked about vacancies. I was wondering, so in effect that suggests that subsurface effects would be picked up because you have a vacancy a few atoms below. It might affect the L delta z equals 0, and then in fact affect the image you take. How deep is this penetration?
Yeah.
Subsurface from the top. I mean, picking on features that might be under involved here.
Yeah. So the question is, since a scanning tunneling microscope really measures local density of states, right? If there's a fluctuation or a perturbation of the local density of states 2 or 3 atoms down into a metal, would that perturbation in the local density of states actually percolate up and be visible in the top layer? And the answer is yeah, it kind of depends on the defect and it kind of depends on the material. So if you have, let's say, a metal and you have an impurity atom buried in the metal, right? The electrons in the metal quickly screen that impurity out. And over a couple of lattice constants, you wouldn't be able to tell the difference, right? But for materials like semiconductors, where the number of screening electrons is vastly reduced, right? You could in fact have subsurface impurities which mimic perturbation in the local density of states, and in principle you could pick that up, right? So this is particularly an interesting question with regard to few-layer graphene, because we're doing scanning tunneling microscope studies of few-layer graphene. We're seeing features on the surface, right? But we don't really know if those features are localized on the surface or whether they're related to perturbations in the few-layer graphene, maybe 1 or 2 layers down, right? We certainly know in few-layer graphene we can see 1 layer beneath the surface. It's a fair question whether you can see 2 or 3. So part of the problem with STM is a lot of these subtleties are being explored at a very high level now, right? The routine use of STM to measure surface topography, that age is gone, right? That was in vogue up until about 1995. right? Nowadays, you have to be a real expert. You have to back up your STM studies with pretty complicated, sophisticated calculations to convince people that you're actually measuring what you think you are. But yeah, in principle, you have a little subsurface imaging. Wanted to comment about 3 early successes of STM, right? These successes relate to the silicon 111 surface, and in particular, the reconstruction of atoms when a silicon 111 surface is formed. Talk a little bit about highly oriented pyrolytic graphite, and then a little bit about gallium arsenide, right? I have to just mention very quickly a little bit of the history behind silicon 111, right? This is an amazing story. In 1959, this gentleman Farnsworth publishes a paper where he notices that there are anomalous structures in the surface of a silicon 111 crystal, right? And as near as I can tell, this was the seminal paper that set off a wave of studies to try to understand in detail what the nature of the silicon 111 surface was, right? So the silicon 111 surface, you have to get a single crystal that has a facet, silicon 111 facet. You have to anneal it in ultra-high vacuum conditions to allow that surface to reach its equilibrium shape. You have to do it in ultra-high vacuum because you have to remove all oxygen. If oxygen reacts with the silicon 111, then it's a different answer. So you're just interested in the bare silicon 111 surface. And the question is, what is the equilibrium arrangement of the atoms on the silicon 111, right? And it turns out that was a big problem, right? From Farnsworth's initial paper in 1959 up until about 1980, I can estimate that there were something like 20 papers a year written every year trying to figure out what was going on in silicon 111. And in 1980, the answer to the question still was not sorted out, right? People were still arguing about that at conferences and meetings. So there's something like 500 publications in the literature trying to sort this problem out, right? And then the exact reconstruction was finally imaged in 1982 with the scanning tunneling microscope. Binnig and Rohr and their colleagues at IBM Zurich in one day obtained this image which showed exactly where the atoms were located. So in one day they solved the problem that was maybe 25 years old, right? Their paper that showed the surface atoms in silicon 111 is this Phys Rev Letters paper from November 1982. I think it's included in the reader, right? There's this picture on the left, which is their experimental STM image. I've added a couple of red lines to try to indicate how that surface is segmented into triangular shaped regions, right? And inside those triangular shaped regions, there are undulations in the image which indicate the position of the individual silicon atoms in this 111 surface. So once they have a picture with atomic scale resolution, they can then start to map in great detail the position of the atoms. And that's how they solved the structure. So experimentally, they had very convincing evidence where the atoms were located. Now, where those atoms were located are now shown in a variety of nice simulations. I took a picture from Trump's webpage at IBM where it shows you in a top view the location of all the atoms in the silicon 111 surface. And it shows you this symmetric unit, this triangular symmetric, actually it's a parallelogram. It's not triangular, it's two triangles stacked one on top of the other. Right, it tries to give you a visualization of where the atoms are with respect to that parallelogram repeat cell, right? Experimentally, of course, well, not experimentally, of course, but I mean, if you just do simple-minded things, right, you can generate a silicon 111 surface, and you would expect to see On the unreconstructed surface, right, you would expect to see a series of hexagons, buckled hexagons, right? That's what's shown here on the right. There's a really nice website where they animate this reconstruction in a very clever way, so you can begin to appreciate all the things that happen once the surface is cleaved and annealed in order to produce this equilibrium structure. So I give the website if anyone's interested in this. So this is what you might expect if the surface is unreconstructed. Experimentally, it's a lot more complicated than that. Again, I just try to make the case that now, because of the STM images, right, we know exactly where each atom is on the surface, okay, in great detail. And it turns out you have to go 3 layers deep in the surface to completely understand where all the atoms go. So when you create that surface and you anneal the surface, the atoms are going to move to their lowest energy configuration, right? That always happens. And how they move, right? They buckle up, they move down, they spread apart. How that moves is really complicated, right? And theorists had tried to calculate that for a long time. There were a lot of models out there, right? I summarize that result in this slide. This is, again, another very famous paper in the early days of STM, 1986, right, where they show different models. In this case, they consider 6 models for the position of the atoms in silicon 111. The models are shown by the solid lines, right? So these are along certain distances of that silicon 111 surface, right? And the bumps in that solid line are the predictions of these different models of where the atoms are going to be located, right? Once Binnig and Rohr does the STM image, they know exactly where the atoms are located along these high symmetry directions. Where the atoms are located are indicated by the dashed lines. And what you see is, of these 6 models, theoretical models that were presented, right, there's only one, this guy Taganagi's model at the bottom, where the fit between experiment and theory is right on. So in one day, obtaining this STM image, they were able to basically solve this problem that had been a major problem in surface science for 25 years. And a lot of us believe this is why they won the Nobel Prize in 1986 for this invention. So the scanning tunneling microscope was only the 2nd Nobel Prize in physics for an instrument, right? And it was immediately recognized the importance of that instrument in sorting out surface features by solving this silicon 111 problem. Okay, so you should at least be aware of that. It's a major advance. At the time, it was really exciting because, most of the people in the business were well aware of how difficult this silicon 111 problem was over time, right? The other thing the scanning tunneling microscope did was it allowed you to image atoms on a reasonably routine basis. And one of the prime materials to do this is this highly oriented pyrolytic graphite, so-called HOPG. This is graphitic material that is comprised of planes of graphene stacked one on top of the other, right? It turns out this material can be easily cleaved and then imaged with a scanning tunneling microscope. And when you image it with a scanning tunneling microscope, you actually can see the individual atoms. So this is some data we've obtained in our lab way back 10 or 15 years ago, where you can clearly see a hexagonal lattice. The bright spots are the location of the atoms. You can do a little bit of filtering so that you can get rid of some of the noise. You can clearly identify the hexagonal symmetry of the atoms from X-ray diffraction studies. You know precisely the spacing of the atoms, right? That number is well established. So you can use this now to calibrate the X and Y motion of your scanning tunneling microscope. So the reason highly oriented pyrolytic graphite is an interesting substrate is that it's atomically flat, the atoms are reasonably easy to see, and it serves as a very convenient calibration in X and Y for the motion of your tip, right? The other big breakthrough that occurred in 1986 was the fact that making use of this local density of states argument that I gave, right? You could actually start to chemically identify different atoms in substrates, atom by atom basis, right? So this was a huge breakthrough, and it was demonstrated nicely by Feenstra's group. Feenstra at that time, I believe, was at IBM in New York, IBM Watson. What he did is he biased the tip with different polarities while he scanned a gallium arsenide substrate. So the gallium arsenide substrate is made up of sublattices of gallium and arsenic. And of course, the local density of states on the gallium is different than the local density of states on arsenic, right? And by monitoring the local density of states as he scanned, he was able to, first of all, image the position of the atoms, but then afterwards he could go back and he could actually color the position of the atoms with either red or blue, depending on whether the density of states was high or low, right? And that allowed him to identify the gallium atoms and the arsenic atoms, right? So in this diagram, or in this picture, which appeared in Physics Today back in '87, the gallium atoms are painted red, the arsenic atoms are painted blue. And this was kind of the first image that showed people that, oh, you can actually do chemical identification with this microscope on an atom by atom basis. So this was, again, a big breakthrough, right, in this business, right? Gold is a very good substrate to image with these tips because gold is very conductive. It's relatively inactive chemically, right? You can produce faceted regions of gold that are atomically flat over microns in dimension. And just to bring home that point, I'll just show a couple of slides of images of gold surfaces. The image on the right is particularly interesting because you can see in that picture there are steps and plateaus, terraces. The height of those plateaus is precisely 0.236 nanometers. That's well established. So you can use the height of those steps to calibrate the motion of your tip in the Z direction, right? So this is again, another example of the type of images, right? And this is, again, just another picture. These are step edges in gold, right? This particular image shows a gold cluster. There are actually two gold clusters that are stuck to the step edge, right? This is an image we obtained in '87 here when we were studying a nanometer-sized gold cluster. This is the days before the STM was connected to a computer, right? So the images have this characteristic line-by-line scan, so you can actually count. If you look carefully at this image, you can count the scan lines that we performed in going from the front of the image to the back of the image. They're all superimposed one on another with a perspective that allows you to appreciate the surface geometry, right? So I guess the question is, why does this all work, right, so well? It's truly amazing. And the answer is everything. Right, the implication is that if you're going to see atoms on the substrate, the implication is that the tip has to have an atom at the apex, right? So that's the only way you can imagine how you can get atomic resolution out of this microscope. So this is a realization that was not obvious in the beginning in the early stages of STM. But as more and more of these atomically resolved images came in, people started to realize that that front atom on the tip was all important in scanning tunneling microscopy. And the reason is, right, the reason is that the electrons in that front tip can be in different atomic orbital states. These different atomic orbital states have different symmetries associated with them. And some of the symmetries that are favorable for high resolution STM are, for instance, the P-type tip or the D-type tip, where the electron wave functions are confined in very narrow regions of space. They actually protrude out vertically into the vacuum beyond the lead atom of the tip, okay? So these diagrams are intended to schematically represent the wave functions of electrons that are associated with different electron states in the front atom on an STM tip. And you can see that if you want to obtain high atomic resolution, as you scan that tip over the substrate, you want those wave functions to be protruding as far as possible in the vacuum, right, in a very sharp, focused way. And so, for instance, an S-type tip, right, which has spherically symmetric wave functions associated with it, would not be a good tip to obtain atomic resolutions. Whereas a P-type or a D-type tip would be much better, right?
So given that you can have all these orbitals present, the choice which one you choose is basically by the bias voltage, right? You can push up, or you can make sure the tunneling occurs from states that correspond to certain wave functions. Isn't that how you control it?
Yeah, so there's two ways to adjust which state you tunnel through. One is by adjusting bias voltages, because you can then have a little bit of control over the states that tunnel. The other is by adjusting the symmetry of the atom on the tip, right? So if you position an atom on a tip and it's weakly bound to the apex of the tip, the wave function associated with that atom would then be more like, let's say, a free atom in space, right? If that atom is tightly coupled to the tip, then maybe the wave function associated with electrons in that atom are more like the bulk electronic states in the tip, right? So somehow adjusting the geometry of that tip atom allows you to adjust in some way the wave function that's present, that's appropriate. Now, it's a very inexact science, right? You cannot tell, even today, what is the front atom on your tip. You can't control that, right? That's one of the drawbacks of STM. No, you really don't know what atom is on the end of the tip, what atom is responsible for the tunnel current. But you can make assumptions, and you can model it, and that's what theorists do, right? They position that front atom in different ways, different geometries, different coordinations, calculate what the wave functions should be, see if those wave functions can then reproduce experimental data. And then they make an inference. It's an inference. They say, oh, the atom on the end of this tip on this day was in let's say an sp3 state, right? It's not very convincing, but that's the best we can do. Yeah.
So the material of the tip also...
Material of the tip is important, right?
Is a typical material. Depends on what I want to see.
Yeah, so the question is, what is the tip typically made from? And the answer is it's usually made from hard refractory metals, because it turns out there's a really large electric field between the tip and the substrate. If you put a 0.5 volt bias between a tip and a substrate that's 1 nanometer apart, you've got a very large electric field in that gap. If you make the tip out of a very soft material, it's gonna disintegrate under the action of that high electric field. So for instance, you might think gold is the best material to make a tip out of because it's inert, right? You might think that. But gold is soft, and when you apply these high voltages, unless you're very careful, you'll rip the tip apart. You'll be pulling atoms off the tip due to the high electric field. So typically, tips tend to be made out of tungsten or platinum iridium, which are much harder materials. Okay? Anything else? clearly the front atom is important. So I like to say the first law of STM is that every good tip ends in one atom. And when you get a good tip, the images that you get are spectacular. If you get a bad tip, you'll spend a whole day and not get anything good. And then the second law of STM is that reliable STM data usually requires ultra-high vacuum, right? Because you want to have a controlled tip, you want to have a controlled substrate, you don't want oxidation, you don't want hydrocarbons settling on the tip and substrate during the course of an experiment. That'll confuse the issue. So you'll find that most STM data today on many materials is done in ultra-high vacuum, right? It's not and the instruments to do these measurements today run on the order of $1 million, right? These are very high-level pieces of equipment. It's a fair question what the lateral resolution of an STM is, right? And I try to indicate that in this diagram, right? I consider two atoms, so I consider a spherical tip of radius r. I consider two atoms. One atom is at the apex of the tip. It's indicated by that little black dot. I consider another atom that's raised by a distance delta z, right, from the apex atom, from the front atom. And in principle, you're going to get tunnel current from all the atoms that comprise the tip, right? It's just that the contribution of the tunnel current is going to depend exponentially on the distance between the atom and the tip and the substrate, right? So, in principle, the whole tip contributes a tunnel current. It's just that the tunnel current tends to be dominated by that front atom, right? And so you can do some simple geometry and you can try to ask the question, what is the width delta x such that the current from the second atom contributes 10% of the total tunnel current, right? You can do some simple geometry. I sketch out the arithmetic. I think everyone can follow it through, but the answer you get at the end of the day is that about 0.6 nanometers, right, or 0.3 nanometers on either side of the apex atom, right? That's where most of the tunnel current is located, right? And so you typically say that the resolution of an STM is typically on the order of, let's say, half a nanometer. You can base it on this simple geometric estimate. That means that the current is confined to a cylinder. For all intents and purposes, the current is confined to a cylinder which has a diameter of about 0.6 nanometers. The height of the cylinder is the distance between the tip and the substrate. That's on the order of 1 nanometer, right? So the total current is confined to a volume of about 0.3 nanometers cubed. That leads us to another question that was puzzling in the early days of STM. STM actually does work in air. And the question is, how can it work in air when they've got all these gas atoms floating around, right? Bouncing off the tip, bouncing off the substrate. Well, the simple answer to why it works in air is that if you just calculate the total number of gas molecules that are contained in a cylinder of volume 0.3 nanometers cubed, right? You get a number on the order of 0.03 molecules per cubic nanometer, right? So, in a volume that's given by 0.3 nanometers cubed, right? You'll find out that there are very few atoms that are actually located in that volume where the current is localized during the time it takes the electron to tunnel from the tip to the substrate, right? So over a long period of time, atoms will work its way in, right? Cause noise in the tunnel current. There'll be scattering events. But usually the electrons tunnel from the tip to the substrate very quickly. And in the time it takes them to tunnel, there's just no atoms. No gas atoms in that tiny volume. So that's a simple explanation that may help you understand why STMs do work in air, right? So in the time remaining, I'd like to real quick skip through some ideas of how to make a scanning tunneling microscope. and introduce some of the technology, because this is going to be important when we talk about AFMs, right? So all scanning tunneling microscopes have certain characteristic block diagram features, and I indicate those block diagram-like features in this diagram, right? Every STM has a substrate, every STM has a tip. The substrate has to be controllable. The position of the substrate has to be controllable in X, Y, and Z. So you need some type of scanner that moves the substrate underneath the tip, X, Y, and also allows you to adjust the distance between the tip and the substrate. Okay? You also often have a signal transducer, something on the tip that takes the signal that monitors the distance between the tip and the substrate, takes that, turns it into a signal that you can measure, right? So for an STM, that signal transducer is a current to voltage converter, right? You measure current, tunnel current, and the tunnel current is typically a fraction of a nanoamp. You can't control on currents easily. You have to control on voltages. So you have to be able to take that tunnel current, convert it into a voltage, and the way you do that is with a current to voltage amplifier, right? There's usually some computer that sends signals to your scanning tunneling microscope. These signals control the XY scan, so that allows you to raster the substrate underneath the tip in a controlled way. There's a tip control signal that allows you to constantly adjust the distance between the tip and the substrate to maintain this constant tunnel current, right? So somehow that has to be in there. And then there has to be some sort of a feedback circuit which allows you to measure the tunnel current, which is recorded in volts by this current to voltage converter, takes that voltage and compares it to a set voltage and allows your feedback circuit to maintain this constant tunnel current. So that's called the Z feedback. So these are like the three essential electronic controls that you need to build if you want to make a scanning tunneling microscope. We're not going to talk much about feedback control in this lecture, but it's going to be an important issue in atomic force microscopy. This is a slide just to introduce you to the concept, because it's going to come back later in a lot more detail. But what you have to do is you have to build a feedback circuit which takes a set voltage that you specify, compares that set voltage to the tunnel current that is measured by your scanning tunneling microscope, and then adjusts the position of the substrate with respect to the tip to make the tunnel current that you're achieving equal to the set tunnel current that you specify, right? So I think mechanical engineers think about feedback circuits a lot more than physicists or chemists. I think electrical engineers think about feedback circuits a lot more than physicists or chemists. But the dynamics of this feedback circuit control a lot of the resolution and performance of a scanning tunneling microscope, and it's important to optimize this feedback loop. So more about that later. The thing I always try to tell new students, even if they're doing AFM, right? Of course, it should be obvious if you're doing STM, but if you're doing AFM, it's a little bit more remote. All the signals, all the images that you measure are voltage images, right? When you see these images in X, Y, and Z, right, those images are really derived from voltages that the computer measures in the course of scanning a tip over a substrate, right? So I always try to encourage students to hook up an oscilloscope to look at the voltage signals that the microscope is generating, because the signal, the image that you get is a voltage image. It's just interpreted in terms of X and Y and Z by software. And if you want to know whether the microscope is working, you almost have to monitor these voltages and start to get a feel for what are good signals, what are bad signals. So I always encourage students to use an oscilloscope to monitor voltages. right? Because it's voltages that are then transformed into images. There's an issue about how to achieve nanometer scanning and positioning without vibration, right? So if your tip is above the substrate, if the tip is positioned above the substrate with a precision of 1/10 of a nanometer, right? How do you adjust its position such that the vibrations of adjustment don't completely destroy the measurement? This was a big problem in the early days, right? It wasn't clear how to do it. Turns out these piezoelectric materials are the method of choice. These are the same materials that Binning and Rohr used in their early versions of the STM. They're still used today. They're much better now than they were. But basically the idea is you can take a piezoelectric bar, you can apply a voltage on 2 electrodes that are attached to that bar. The voltage that you apply sets up an internal electric field, and that internal electric field then causes the length of the bar to change. So the length of the bar goes from L to L plus DL, right? Where DL is given by the voltage that you apply, V naught, times a geometric factor that's related to the geometry of the bar, times a coefficient, a piezoelectric coefficient that's a property of the material that the bar is made from, right? So if you want to know how much the bar expands when you apply a voltage, let's say 1 volt potential, you got to know the ratio of L over H, you got to know that piezoelectric coefficient, right? And typically you'll get for bars, for piezoelectric bars, typically you'll get about 0.5 nanometers per volt applied. So if you apply a volt, the length of the bar expands by about 0.5 nanometer, typically. These piezoelectric bars were quickly replaced by these quadranted piezoelectric tubes. These piezoelectric tubes are probably used in 90% of all the microscopes that you'll find on the market today, right? So the scanning capabilities of the microscope are achieved by putting voltages on various quadrants of this piezoelectric tube. And depending on the quadrants that you bias with an external voltage, the tube will slightly bend one way or another, right? So if you want to raster a sample in X and Y, it requires you to produce a sequence of voltages to the X and Y quadrants of this piezoelectric tube, and then the piezoelectric tube bends faithfully. Well, not 100% faithfully, but it bends. Right? Not by a lot, right? Because the scans typically are on the order of a few hundred nanometers. And STM scan ranges are a few hundred nanometers, right? So this is the technology that's been evolved to scan samples and position tips without vibration. It doesn't require mechanical gears. It doesn't require you to put your fingers on something and adjust the knob, right? All you have to do is apply a voltage. So that's a real useful technology. This is an example of the feedback circuit that is used in scanning telemicroscopy. It involves an operational amplifier indicated by that yellow triangle. Here, physics students and electrical engineers, right, they can design these operational amplifiers to do the required feedback signals. Basically, what that operational amplifier does is it compares the tunnel current, which flows between the tip and the substrate. That tunnel current is converted to a voltage by an I to V converter. The gain of that I to V converter is on the order of 10 to the 9th. So if you get a nanoamp of tunnel current, you typically get a volt out. That's what that 10 to the 9th gain means, right? 1 nanoamp equals 1 volt. You can then compare that 1 volt signal, that voltage out of the I to V converter, you can compare that to a reference voltage that you set. And what this feedback circuit does is it basically adjusts the position of the tip, let's say by a piezo tube scanner, right? in such a way as to maintain a tunnel current that matches the reference set voltage that you specify. All right, so every scanning tunneling microscope has this embedded in it somewhere. And the trick is to make the feedback circuit as fast and accurate as possible, so that if there's a sudden change in tunnel current, you want to accurately adjust the tip so as to compensate for that change in tunnel current, right? Same thing will happen in AFM, except in AFM we're going to be monitoring deflections of cantilevers. And we need a slightly different feedback circuit, but it's the same principle. There's a big issue about vibration damping, right? Because if you're trying to maintain a constant gap between a tip and a substrate, and you want that gap to be constant to better than a nanometer, let me tell you, anybody walking down the hall, any truck that drives along the sidewalk, elevators that go up and down in the building, fans that kick on, anything like that will cause the floor to vibrate and shake, and will screw up the positioning of the tip above the substrate when you're talking about nanometer accuracy. So how do you actually make these microscopes work? The answer is you have to build in a very high level of vibration damping between the floor of your building and the actual microscope. All right. So when we built these things in the early days back in the 1980s, we actually would go around the physics building with a little seismic vibrometer, and we would measure the vibrational spectrum of the floor in different labs, trying to find out, and we did it at night just to try to find the quietest room. And we did that in about a dozen labs until we actually located one where the vibration of the floor was the smallest of all the floors that we could find. And that's where we then located our STM, right? The vibration control can be as simple as a sequence of springs between different stages, right? I tried to make the case here that if the floor vibrates by an amount delta Z naught, and you connect a platform to the floor, then the platform vibrations will be attenuated by a factor alpha times the vibrations of the floor, right? So that's for one stage. If you build in multiple stages of vibration, then you get an alpha to the n advantage in principle. So if you build in 2 or 3 levels of vibration isolation, each level of vibration isolation helps you into a good approximation. If you build in n levels, you'll get an alpha to the n damping of the floor vibration. So typically in the early days, we'd build in 3 levels of vibration isolation in these microscopes, right, to try to isolate the vibrations of the floor from the instrument. And even then, we'd only be able to make it work once a week, right? There's a few well-known limitations of these piezos that you should at least be aware of, right? Because these limitations often cause you to misinterpret your images. And I'll just tell you that there is this thing called creep, which basically means that if you apply a square voltage pulse to a piezo bar, you would expect the piezo bar to instantaneously respond to that voltage and change its length instantaneously to a new value. But the sad truth of the matter is it doesn't work that way. Right? When you apply a voltage pulse, right, it takes a certain amount of time for the bar to adjust its position. So that gives rise to this creep behavior, right? And this creep behavior is gonna be an artifact that often shows up in the process of interpreting scanning tunneling microscope scans, right? Another issue is involved in the apparent width of small objects, right? I think anybody can understand that if you scan a tip of finite radius over an object which is small compared to the diameter of the tip, there's going to be a convolution effect, right? The shape of the tip is going to influence the image that you obtain. So this gives you a very simple geometric way to estimate how wide an apparent feature will appear if you scan over it with the tip whose radius is r sub tip, right? Turns out the apparent feature width, just following the simple geometry here, the apparent feature width is 4 times the square root of the radius of the tip times the radius of the feature. So the radius of the feature is always greater than it actually is when you image it with these scanning tunneling microscopes. And this is a rough and ready way to sort that out. Right? How do you make the tips? Well, there are two ways. One way is electrochemically etching. What you do is take a tungsten wire, submerge it in a solution, apply a voltage between a carbon rod and a wire, and an actual tip forms at the meniscus between the etching solution and the air. Right? It takes a few minutes for this electrochemical etching to occur, and the bottom part of the wire literally drops off, and what's left is a sharp tip. The other way is just to cut a metal. Just take a piece of, in this case, platinum iridium wire, cut it, right? In the process of cutting it, you're going to produce these little mini tips, and these mini tips are very sharp, and they're very useful for scanning tunneling microscopy. So I think I'm basically out of time, and I'll have to stop right here. And if you come back on for the next lecture, right, we'll discuss a few more advanced topics of STM just to give you a sense of how this microscope has pervaded science, technology, and engineering, and why it's so popular today.